Yeah, this is the example there, classes and processing example we wrote in the class. If you want to clone the repository, you should know how to clone the repository if you were in the lab last week. You can just clone the repository and find the example. It's under the folder classes, okay? So clone the repository is better. If you remember how to clone the repository, git space clone, and then you paste in the URL from the repository without the /tree master bit. So just like http://git pub.com/scooter500 /DT228-OOP-2015. If you type that, you'll clone the whole repository and you'll get all of the files, everything that we've worked on since the start of the year. And if you go in, navigate into the processing folder, into classes, you'll find this example, which is the one that we worked on last week. So, yeah, just to remind everybody, so lab test tomorrow. If for some reason you can't attend the lab test, you need to fill out a PC1 form and submit it with supporting documentation, because otherwise this is part of your assessment for the course. So you have to be there tomorrow for your lab test. And the lab test is different to last year's lab test. Obviously it's a different problem, but it's sort of related in that you have to draw some graphs, you have to make some classes to encapsulate certain information, and then there's just some general processing drawing code in there as well. So it's similar to last year's but different. The other thing as well is your first assignment deliverable is due on Wednesday, so I need your Git repositories and a README file and your data set submitted by Wednesday. There's a Git link, there's a Google Docs link up on the assignment page now, okay? So everyone needs to get that submitted. So, the plan for today, first of all, PVectors. And then we're also going to do stuff like classes. In classes we'll talk about constructors, methods and fields. We'll just put classes up there in encapsulation. Oh yeah, object references. And then finally inheritance. So that's kind of the plan for this week, right? So why don't we just have a little recap? Is everybody happy with, I'm not going to go through Git stuff again. There's 2 YouTube videos now. There's one from last Friday's tutorial and also the video from last week's class. If you're not too sure on Git, you can watch back either one of those. At some stage, you need to bite the bullet and read the first 3 chapters of the Git manual. There's really no substitute for that. That's the best way to learn Git, okay? So yeah, just do that, okay? Yeah, so let's look at this example. This is the example we were working on the last day in the class, okay, on Monday. And we'll just take a quick look back at this code before we start modifying this code first of all. Okay, so first of all, when we run this little program, we see that we have a thing on the screen. And so whenever you have things on the screen, it makes sense to try and encapsulate the behavior and the state of that particular thing onto the screen into what's called an object or a class. So we have this little thing on the screen that can move around in response to the keys. And so to encapsulate that, we made this class called ship. And these are the fields. This is a special method here called a constructor. Okay, this is a default constructor. What's typically a constructor used for? Can anyone tell me? Yeah, so it'll be typically to give like initial values to the object. We make a constructor. And you can see this constructor here, what it's doing is it's giving the initial values to x, y, w, and half w, which are all fields in the class. Okay? And then this down here, what do we call this? This update is called a method. Okay, so when you have code which is attached to an object, it's called a method. And methods typically are describing what the object can do, and then fields describe what the object is. So these fields basically say that every ship contains an x, a y, a w, and a half w. And then if I instantiate that, I get access to those fields by using dot. So dot gives me access to the fields which are members of the instance of the class. Alright, to instantiate a class, at some point you have to go equals new and then you decide which of the constructors you're calling. In this example here, we only have one constructor. On Friday we made a parameterized constructor, and I'm going to talk about, we'll do a parameterized constructor for this class as well. But what happens here is you go ship equals new ship. What will that do is it goes and allocates that memory required to store those fields for the ship, right? And now ship references an object of type ship, the ship with a lowercase. Down here you can go ship.update and ship.render. So these are calling the update and render methods on the ship instance. And what would happen if I forgot to do ship equals new ship? What kind of error would you get? You get a null pointer exception, okay? So whenever you have these what are called reference types in Java, or objects or classes instance, unless you actually at some stage go equals new and then call a constructor, the object just points to null. It points to null, and so you get a null reference exception. Alright, it's quite common when we're making classes that classes keep references to other classes. Alright, so first of all, looking at this little ship class here, it would seem that we could probably group that x and y together, couldn't we? You know, because x and y, what will we call the x and y of the ship? It's the ship's position. Okay, so let's make something to encapsulate the x and y together into another thing called its position. And you can understand, like in the real world, very often we group numbers together, right? This is another example of encapsulation. And this year we're going to group the x and y together. Now, sometimes when you group numbers together, okay, you can use those grouping of numbers in all kinds of different contexts, right? So let's say, for example, that x and y, it turns out there's actually a built-in class in processing which does group that x and y together, and that class is called a PVector. Can I just do a quick check here? How many people did honours maths for the Leaving Cert here? How many people did ordinary level maths for the Leaving Cert? Yeah. Okay, so just a quick check. Did you guys, how many people have heard of a vector? If you did honours maths, you would have certainly. If you did ordinary maths, did you ever hear the concept of a vector?
Heard of it, but didn't do it.
Heard of it, but didn't do it. Okay, so a vector is nothing terribly complicated. Apart from a vector, is just, mathematically a vector is described as just a list of numbers. Okay, the number of elements in that list is called the dimensions of the vector. Okay, so PVectors in processing always have 3 dimensions, but you can use 3 or 2 dimensions when you're using a PVector. And for this 2D program, all we're going to do is use 2 of the dimensions. Okay, have a guess what you think the fields are called inside the PVector for the 3 dimensions. Exactly, yeah. So every PVector has got an x, a y, and a z field associated with it. You don't have to use the z, and in fact, for this 2D example, we'll just reference the x and the y fields inside the PVector. Now, interesting question. We have something here which is a PVector. It's got an x, y, optionally a z. What are we going to use it for apart from position? What in the real world requires not just one number but a list of numbers, and ideally something like with either 2 or 3 dimensions to encapsulate? What sort of quantities would require that? Huh?
Coordinates.
Coordinates, perfect. Okay, so number 1, things like positions and coordinates. They will all require more than one number or a list of number, and like I say, it makes sense to group those numbers together. Anything else in the real world?
Trajectories.
Trajectories, okay, so stuff like directions. Okay, anything else? Trajectories. What are we talking about when we're talking about trajectory? We're talking about an object's moving, yeah. So what describes how an object moves with respect to time? Next one, yeah, acceleration is how something else changes with respect to time, but how something moves with respect to time is called its velocity. Okay, so we can also have a direction vector, you can have a velocity vector. Why do we need 2 numbers to describe velocity? Why can't we just use 1? Why can't we just use speed?
Magnitude and direction.
Yeah, exactly, because things don't always move in like a straight line. Well, sorry, things move in a straight line, but things can move in a straight line in a particular direction. So if some object is located here, I can say that the object moves 3 units, but that 3 units can be anywhere within this circle. Right, so when you describe the 3-unit movement as a vector, in other words saying it moves a certain amount on the x and a certain amount on the y, then all of a sudden you have that, which is now a vector. 2 numbers which tells you how an object moves with respect to time. That's called velocity. Anything else? Somebody mentioned another concept there. What's velocity measured in?
Meters per second.
Yeah, meters per second. What's position measured in? Meters, perfect. Okay, so we describe that in meters. Velocity is in meters per second. Anything else that we might need more than one number? Last time I checked, I think time only is actually one number because it only goes in one direction. So I think time is interesting. Time only we can represent using a scalar, and time is just seconds. So don't worry about the vector versions of time, at least not in this universe. Any other ones? Any other things that we could use?
Density.
What's that?
Density.
Say again?
Density.
Density. Yeah, I think usually when we're doing simulations, we might use one number, kind of like the object mass, to describe something like that. Anything else? Acceleration. Yeah. These are all things that we can use 2 numbers or multiple numbers to describe. Why acceleration? Because acceleration is a directional quantity as well, right? When you're accelerating, that means you're changing velocity in a particular direction. What's the unit of measurement for acceleration?
Meters per second.
Yep, it's meters per second per second. So it's how many meters per second you change every second, right? So all sorts of quantities like this that are required to implement any kind of real-world physics. We require this structure called a vector to encapsulate, right? So we want to modify this program a little bit so that we'll use vectors instead of using x and y coordinates. In fact, let me just write a little p-vector program first of all, just to illustrate some of the properties of p-vectors. Let's just create a new sketch here. Just going to do some stuff with p-vectors so we can see what they do, right? P-vector. This is what a p-vector looks like. You go p-vector and you call it A. P-vector is a class, right? The same as the types of classes that we're making ourselves. A p-vector is a class which is built into processing. So now A is going to be an instance of the p-vector type, right? P-vector B. So now I have 2 p-vectors. Now when we made our ship object, what did we have to do to actually allocate memory for those? We had to call new. You have to call new. At some stage you have to call new. Otherwise, if you try and do something like print out the values, if you try and print out the value of A, or if you try and print out any of the components of A, is that giving me an error because it's not allocated? Local variable may not have been initialized, right? So my program won't even compile because processing quite rightly has identified the fact that I've forgotten to allocate any memory for A and B, so it won't even compile. So if you try and do something with A before allocating any memory to it, it won't even compile. So at some stage you have to go equals new p-vector. Alright, so that will allocate a new object of type p-vector and assign it to the variable A. Up until this point, A doesn't have any memory associated with it. So there we go. I've got 2 p-vectors now, A and B. And you can print out the values for A. So obviously, what do you think the default value is going to be for A.x? It'll be 0. It'll be 0, okay? Because A.x is actually of type. What will its type be? It's a float, okay? A.x is of type float. A is of type p-vector. So when you try and print out A initially, its value will be 0. So some things that you can do with p-vectors, there's another constructor which takes 2 parameters and it gives the initial values to x and y. So you can also instantiate a p-vector like this, and you can give it the values of 10, 10. So there's p-vector B now has the value of 10 for the x and 10 for the y. And this is an example of a parameterized constructor. So, that's just passing in 2 arguments into the constructor. So now B is going to have the value of 10, 10. Alright, you can also do, obviously you can access the fields individually. You can go A.x equals 20. So now that's just going to change the value of the x component of the p vector a to have the value of 20. So now when you go print ln a.x, it's going to print out the value of 20. Okay, now without me even explaining this, let's try an experiment here, right? Okay, have a look at that code and tell me what you think is going to get printed out before I even explain what that add does, just to see if you can intuitively understand this. Have a look at the code up there and tell me what's going to get printed out, the very last line of code. What will it print out? Would you have 30 10? Okay, so just the very last line, a.x is going to print. So, okay, just the very last line. Okay, so a couple of options here. Some people suggest it's going to print out 30, 30. Any other suggestions?
30.
Just the word, or just the number 30. Any other thoughts? What's the other one? 20, 10, 10. So that's 20 for the first A, is it? No? Or just the last line? If I comment out these other lines here, let's see.
Oh yeah.
To make it clear what we're doing. Yeah, what do you think now?
10.
10 is another possibility. Anything else? Minus 100? Probably not. Okay, let's take a vote then. Who wants to go for 30, 30? One. Who wants to go for 30 by itself? Alright, that's kind of likely. Who wants to go for 10? Alright, okay, no problem. The correct answer is it's going to print 30. And the reason why is because what adding two vectors means is that you add the x's together and that you add the y's together. If we were to look at the implementation of that method, it would be very, very straightforward. All it would do is take the other vector, and you would see that it just takes the other vector and adds the x component of the other vector to the x component of this vector, and then adds the y component to the y component of the other vector. Adding vectors mathematically, okay, means that you add the x's together and that you add the y's together. And there's lots of reasons why you would want to add vectors together. To give you a very simple example, okay, let's imagine that you're stuck on a desert island and you're initially located at, let's say you're stuck on a desert island and your initial position is the vector 10, 10. This is your vector coordinates. Let's say we'll stick to the processing way of doing coordinates. And then let's say you're given a set of instructions to find a treasure. Alright, and let's say your instructions are first of all to follow 3 meters to the right, 2 meters to the left, then minus 5 meters to the right and 7 meters to the left, and 10 meters to the right, 3 meters to the right, 2 meters down, minus 5 meters which is to the left, and then 7 meters, and then 10, and let's say minus 3. Okay, and then after you've walked out all of those different directions, then you reach the treasure. You follow the problem I'm trying to express here? So this is telling me all the different directions that I have to walk. First of all, 3 meters to the right, then 2 meters down, then minus 5 meters, so in other words 5 meters to the left, and then 7 meters down, and then 10 meters and 3. So you guys work out what you think the location for the treasure is. What do you think the location for the treasure is? Okay, any thoughts?
18, 16.
Okay, so some people think it's 18 and 16 is the location for the treasure. Any other suggestions? How did you work it out? You just added them all up together. Okay, so the hard way or the long way to do this is to start at position 10, 10, then go 3 and 2. So if we move 3 meters over here and then 2 meters down here, we end up at the position 13 and 12. Okay, and then we have to move minus 5 and 7 meters from there. So then we go minus 5 meters this way and then 7 meters down, and we end up down here. So this is going to be at position 13 minus 5 is going to be 8, and then 12 and 7 is 19. And then 10 meters and minus 3 meters, so you go 10 meters this way and minus 3 meters up here. So then this is going to give us 18, and then 19 minus 3 gives us 18, 17, 16. 18 and 16. Okay, so I could have done, I could have done this like this. Gone walk here, down to here to this one. Followed these directions meticulously, and then followed these directions up here meticulously. What would have been the clever way to solve that problem? Instead of doing, if you were there with a computer scientist who just understood vectors and just had a class on them, somebody who didn't just have a class on vectors, what would the guy or the person I should say, who's just learned vectors do? They would just add them all and go straight to the destination, right? So if you were to add all of these up together, you go 5 minus 3, this is minus 2, and then 10 is 8, and then 2 and 7 are 9, minus 3 is minus 6, 2 and 7 are 9, minus 3 is 6. So you take 8 and 6, and then you just add 8 and 6 to this, and it will bring you straight to the destination without having to go through any of the intermediate steps. Do you see that? Everybody?
Yeah.
So that's what adding vectors means. Adding vectors means that you add the x components together and the y components together. So there's a method here called .add. There's lots of other methods, right? There's a method here called .mult. But the method .mult doesn't multiply two vectors. What it does is it multiplies a vector by a single number, a scalar. The scalar is called a scalar because what it does is it changes the size of the vector, but it doesn't change the direction of the vector. So if you take the vector A there in this example here, and I go .mult 3, what do you think is going to get printed out?
60. 90.
90. Yeah, so what it will do is .mult multiplies each component of the vector by a single number. So .mult will multiply the x component by 3 and the y component by 3, and you end up with a new vector which has got the value of the x's and y's added together. You can also call .sub, and .sub will subtract one vector from another. So we can add, multiply and subtract vectors. There's a couple of other interesting things with vectors. First of all, if you take any old vector, we'll say the vector 10, 10, there's a concept of the length or the magnitude of the vector. So the magnitude of the vector is described as the distance from the origin to that vector. I'll just write that up. The magnitude is the distance from the origin to the vector. So, let me give you a simple example. First of all, if you take the vector 0 and 10, what would be the magnitude or the distance from the origin to that vector? Yeah, definitely, it's 10. Okay, so the distance from 0, 0 to the point 0, 10 is 10. If you were to pick that one, 10, 10, what would the distance there be? Or how would you calculate it?
Pythagoras.
Yes, you'd use it by Pythagoras, okay? So, if you to plot that here, there's the vector 10, 10. The distance of that vector, or the length of that vector, is the distance from there to there. And of course you would use Pythagoras to calculate that. Make that a right angle triangle. Then this becomes a hypotenuse, the distance you're trying to calculate. So you calculate that from this vector 10, 10. How would you calculate the distance or the magnitude of that vector? Mathematically, what would you do?
10 squared plus 10 squared.
Yes, perfect. Okay, so it's just the square of the x's and the square of the y's, and you get the square, the x's and the y's, you square them, add them, get the square root. So it's just Pythagoras. If you don't understand, or it's not clear to you why you would do that, then draw a right angle triangle yourself, and you'll see that you just take the x to be squared, the y to be squared, and that gives you that, the hypotenuse, or the length of the vector. So it's the square root of x squared plus y squared. Okay, so in processing terms, you go a dot, is it dot mag? Yeah, a dot mag. That will return you the magnitude or the length of the vector as a single number. And it does that by getting the square root of the x's, the square root of the to be squared, and the y's to be squared. And there we go, that's the magnitude of that vector. Sometimes we want to take a vector and we want to what's called normalize the vector. In other words, make the length of the vector equals to 1. So that retains the direction of the vector, but it makes the magnitude equals to 1. So you lose the size of the vector. And it's quite useful that you have vectors which are of length 1. Because I want to, for example, I'm moving in this direction at 5 meters per second. So you can take the direction vector multiplied by the speed and it gives you the velocity. In order to do that, you call dot normalize. Spelled with the American spelling. So mathematically, and it's not too important for this course, but what that does is it calculates the length of the vector and divides each component of the vector by the length of the vector. So if you have the vector 10, let's say you give you a simple example, if you have the vector 0 and 10, and you normalize that, what vector do you end up with? Remembering that it retains the direction, but the length becomes 1. So the vector that goes in the same direction, or that points from the origin in the same direction as 0, 10, but is of length 1 is going to be the vector 0, 1. Obviously it's the vector 0, 1, right? Because that's of length 1, and it's in the same direction as the vector 10, 10. So that's normalizing a vector. There are versions of these, I wonder, do we need to mention it just now, or can we do a little bit of yeah, let's see, should we do an example? Should I give you guys a little program to work on now so we can just make sure everybody's clear on all this stuff? I've been talking for too long, I think. Yes, I think I'll ask you to write a little, or I think I'll give you a little program and get you to work out what the answer is. Yes?
What's the difference between a mag and then just printing that the magnitude of the function? If you're just printing, like if you're having a mag compared to just printing that.
Oh, great question, yeah. This exactly here, it doesn't do anything useful whatsoever. What you'd probably have to do is go something like float m equals a dot mag, because that's a method which does a calculation and then returns a value. So it doesn't actually affect the vector by calculating the magnitude. All it does is calculate the magnitude. So unless you actually took the return value and did something with it, then the code is kind of a bit pointless like that. Good example. Okay, good, well spotted, right? So, okay, I think I'll get you to write something with vectors, or I'll get you to do something with vectors, right? Let's take a little example here. Here's vectors A and B. Let's say I go A equals new P vector can do this. We'll see in a minute.
Try that.
Okay, there's just a short sketch that does nothing terribly interesting, but just want to make sure that you understand these vector operations before we go on. Yeah, well, you just take a couple of minutes and without writing on your code, but just on pen and paper, work out what's going to get printed for A and B at the end there, okay? Just to make sure you're completely sure about how all these vector operations work. And just don't type the program as such, you don't need to run it to get the answer. Just work it out on pen and paper. So A dot mult2 takes A, and A starts out at 2020, so A becomes 4040. And then A dot add B, so let's write up A over here, and a box for A and a box for B. So A starts out at 20, 20, and B starts out at -5, -7. Okay, so then A dot mult 2, so basically takes this and makes this equals to 40 comma 40. And then A dot add B, so we take B minus 5 minus 7 and we add it to this. So minus 40 then becomes 35, and then this becomes 33. So that's A dot add B. Then B dot add A takes B and we add the contents of A to it. So minus 5 plus 35 becomes 30, and then 33 minus 7 becomes minus 20, sorry, becomes 26. 26, yeah? So that's A dot add B, and then we have A dot sub 220. So I take A, 35 then becomes 33, 33 becomes 31. B dot mult 3 takes B, so this becomes 30 becomes 90, and 26 becomes 60, 3 6s are 18, becomes 78. Correct? Yep. Okay, and then B dot sub A, so then I take B and I subtract this from it, so 90 becomes 57, 60, 78, 90, 57, and then 78 minus 31 becomes 47. Yeah, 57, 47. Yeah, 57, 47. Does that look correct? Okay, everybody, does everybody know how to add, subtract, multiply, and divide vectors? Wonderful, excellent. Okay, I'm going to put one more small problem up here, and I want you to take a guess at what you think is going to happen here, right? Okay, so I've just set the x and y components of A and the x and y components of B to be those various numbers. Alright, take a look at that last bit of code, and I know it's Monday morning and everything, but this is probably the most important thing you're going to learn today. So take a look at the above code, and without running the code, have a guess and see what's going to get printed out for b.x without running the code. So study the code very carefully, take it down if you need to. A.x equals 10, A.y equals 10, B.x equals 20, B.y equals 20. So A has the value 10, 10, B has the value of 20, 20. Then we go B equals A, and then I change the value of A.x, and then I print out B.x. So look at the code very carefully and make sure that you understand at least what's the sequence happening in the program. Yeah. Yeah, so I'm overwriting the previous values that were stored in A. Okay, without running that program, what's going to get printed out? 10. Okay, so a couple of options here, right? Number one, how many people think 10 is going to get printed out? Okay, any other suggestions as to what might get printed out? Okay, so 40 might get printed out, possibility. Anything else that might potentially get printed out that anyone has got any theories about? 30 might possibly get printed out. Okay, so let's take a vote then. How many people vote for 10 again? Put up your hands. Right, how many people vote for 40? Nope. How many people vote for 30? Okay, the correct answer is... Let's run the program and see. The answer is 30. So that's kind of counterintuitive, isn't it? Why? Okay, I'll explain why. And like I said, this is the most important thing that you're possibly going to learn today. So it's very important that you pay really close attention to this bit of today's class. This is the most important thing. I have a small diagram which will explain what actually happens here.
Oh, maybe it's pointer.
First of all, let's change the code very slightly here, right? Let's say that I go float A, float B. In other words, I make A and B what are called primitive types. They're primitive types. They're standard old ordinary floats. You go A equals 10, B equals 20. You go, what have we got there? With B equals A. B equals to A. And then you go A equals 30. And then you print ln B. If these were floats, look at the code there. This is basic old plain old floats that we've used so many times before. It's pretty obvious what gets printed out in this example here, isn't it? So you go A and B. A is the value 10, B takes the value 20. So A is my little box for A takes the value 10. B over here, my little box for B takes the value of 20. And then you go B equals A. So this takes whatever is in A and copies it into B. So B takes the value of 10. And then you go A equals 30. So then when you go print ln B, what gets printed out? Obviously it's 10, isn't it? Does everybody understand this floats example here? If you want, you can take this little example then, because this is an example of what's called a primitive type in Java. And this is how we would expect our classes to operate, but they don't, in fact. Alright? So, what's that? It did, because that's where we're using classes up here. I'm showing you this is how it would work if it was a float. If they weren't instances of a class, if they were just ordinary floats. Exactly, this is why everyone intuitively felt that 10 should get printed out, because this is what we have been dealing with up until now. Does everybody understand this example? We'll do the same thing with classes, and I'll show you how it works, right? Huh? Yeah. I'll rub this example out here. Okay, so we'll do the same thing again. So first of all, I have a.x is equals to 10 and a.y is equals to 10. So now I have this aggregate object over here called a, and it has the value of 10, 10. Next thing that happens is b.x equals 20 and b.y equals 20. So now I have this other object called b, and b takes the value of 20, 20. Alright, here's the important bit. And like I say, this is the most important thing from today's class. This example here, we go b equals a. If these were just floats, what would happen? I would copy the values from b into a. But that's not what happens, because these are objects now, and objects work differently to primitive types. What actually happens here is, I'm going to rewrite this slightly, I have this thing called a, which points at this block of memory. I have this thing called b that points at this block of memory. When you go b equals a, what happens is b's pointer now points at a. So now there's one object with two things pointing at the same object, right? When I go a.x equals 30, what happens? Because b and a are pointing at the same object now, I'm changing b every time I change a as well. Which leads to an interesting question. What happens to this guy over here? Yeah, all of this is going onto the heap. Alright, all of these are created on the heap. That's where objects are created. But what happens to this guy? The original values for b. What happens to this little block of memory that I've allocated? It goes into the trash. The technical term for that in Java is called? Anybody know? You said it? Garbage collected. It gets garbage collected. Okay? So that object, there's a low priority, what's called a thread in Java, constantly running in the background, and it's looking at your code to see, have you allocated some objects that you're no longer keeping around, that there's no longer any reference to, and it goes and frees the memory. If you're doing this manually in C, you would have to write the code free. Remember free and malloc? But in Java, because of how Java works, every time you no longer reference an object, it will get garbage collected for you. Isn't that an interesting thing that we learned? Alright, how are we doing for time? 11:03. Yeah, I think we'll take a short break now, and when we come back we'll apply all of this vector stuff to the spaceship class that we just made, and we'll replace the x and y and the movement code with code based on vectors instead of code based on x and y. And hopefully we've learned this really important concept in Java. So I don't know if you've had a chance to have a look at this, but what we're trying to do now is basically, we know how p-vectors work, right? We know how to add and subtract and multiply and divide multiply p-vectors. We can take this example over here, which is the ship example that we previously made, and let's start replacing some of these. Let's start replacing some of these fields. Well, replacing one of the fields with a p-vector. Now our aim here, by the end of this class, we'll certainly get this done, is to be able to get the ship to move around in response to the keys, but also to turn and move in the direction which it's pointing. It's much easier to do this with vectors. So let's take my x and y here and replace it. This, by the way, if you've ever come across this term, it's very common that you write the program one way initially based on what you know, and then you come back and rewrite certain aspects of the program. And does anybody know what the term for that is called? It's called refactoring. So we're going to refactor the program now, right? So instead of having x and y, I'm going to have a p-vector called pause. So in my constructor, what's the first thing I need to do with pause? I need to allocate some memory for it using new. So you can go equals new p-vector. So I could just do that, or I could actually pass in the x and y coordinates into the constructor of the p-vector. Why don't we do this? Let's do this entirely correctly, okay? Let's make a parameterized constructor of our own. Okay, I'm going to make a second constructor here. This is the constructor that's going to take two parameters. On Friday we talked about this, but it's just to remind people, it's possible to have any number of different constructors for a class, so long as each constructor takes different parameters. This constructor here is going to take an x and y parameters, okay? Okay, so what's going to happen here, if I call this constructor and pass in the x and y coordinates, it will construct the p-vector based on the two coordinates that have been passed in there, alright? And then that's x and y. W is equals to 50. Why don't we make that a parameter as well? Alright, so I have pause, and now I have W parameter, and I have a field called W as well. So now what I want to do is disambiguate. I want to be able to say the W field of the class is assigned the value of the W parameter. Does anybody remember how you do this from Friday? Because I need to disambiguate. So I use this. Yes. Okay, so that disambiguates between the this, which is the field, and the this, which is a parameter. So this.w equals W, and let's do the same for half W. Cool. Okay, obviously in the second example, the this.half do, the this is optional there, because there's no disambiguation required. There's no other variable in scope called half W. The only one that's in scope is the field. So this is actually optional there. Now look at my default constructor. I'm going to modify my default constructor. And what I'm going to do for my default constructor is I want to say you can see that there's a bit of duplication here, right? I have some code there in my default constructor that's already in my parameterized constructor, so wouldn't it be nice to just say, if you call a constructor with no parameters, then just call the constructor with 3 parameters and pass in some default values. And you can do that in processing as well. You do that in Java, I should say, by using this keyword. Alright, so this is an example of, I'm going to put a note up here as well, this is an example called constructor chaining. So constructor chaining means calling one constructor from another constructor, and it's a way of avoiding duplicated code. Right, you can see what's happening there. If I called ship with no parameters, then this keyword here actually means something slightly different. It means call the other constructor, and the keyword this now is used to mean something different. It doesn't refer to the current object, but what it's used to say is actually call the current constructor, or call the constructor that takes 3 parameters. How it knows to call the one with 3 parameters is because there's 3 parameters here, and these 3 parameters match up over here. So now, let's modify key pressed. So if the key is W, what do I want to do? I want to move in the direction of my Y, so I'm going to go pos.y minus minus. Alright, so wherever I had X and Y, I've replaced it with pos.x and pos.y. And in my render code, wherever I have X here, I'm going to replace it with pos.x and pos.y, pos.x. Okay. Alright, so that's it. That's my code refactored. So now I'm using a PVector instead of using X and Y components individually. Of course, after writing all of that code, this program is still going to do exactly the same thing. So we haven't really moved things along, even though conceptually we've moved things along a little bit. In terms of the functionality here, it's going to do exactly the same. That of course should be pos.x plus plus. Okay. Alright, so is that okay with everybody? That's the PVector code replaced, and that's the first step. Next thing we might want to do is we want to make our ship be able to rotate and then point in the direction in which it's facing. So, I need to explain some stuff to you, which is kind of PVector related stuff. Alright, so you probably remember, hopefully you're going to remember this anyway. So, let's say that my ship is located at some position in the scene, and there it is there, and I want my ship to be able to move around. Alright, so if I wanted to move straight up, what do I add to the X and Y of the PVector to make it move straight up? The X, what do I add? Nothing. And if I want to make it move straight up on the Y, what do I do? Minus 1. Alright, does everybody understand that? That's to get it to move straight up in this direction here, yeah? If I want to get it to move straight down in this direction, what am I going to add to the X? 0, and to the Y? 1. And then if I wanted to move in the X direction here, I add 1 to the X, 0 to the Y. And then over here, minus 1 and 0. So first of all, we can see that the direction of movement is also, or can also be a PVector. Do you see that? So the direction of movement can also be a PVector. And if I just go dot add my direction vector to my position vector, that will have the same effect of doing pos.x plus plus and pos.y plus plus. Everyone see that? Okay, so let's refactor the code again. Let's add one more field up here called direction. In fact, let's call it forward. So now I have a new p-vector called forward. And in my constructor, let's give my forward vector a value. So it'll be the vector 0 and minus 1. Because that's the way forward is if I don't do any rotation on my ship. And then down here, instead of doing pos.x minus minus and pos.y and all the rest of it, let's write this in vector terms instead. Let's go pos.add forward. And let's also do pos.add forward for all of the other cases. I wonder, does it make any sense to do that? No, let's just get rid of some of this code here, right? We'll comment this code out for now, because there is something we need to do here before this is all going to fit together. But can you see that when I go pos.add there for w, that's the same as going pos.y equals pos.y minus 1, or pos.y minus equals to 1. Can everybody see that? So I've just changed my, my first line there to be a vector version of it. Okay, so moving in these ordinary, like, 4 cardinal directions is pretty straightforward, because it's very easy to work out the vector that you would add to the position to get it to move, right? On the other hand, imagine I wanted my ship to move in this direction here. Then what do I need to add to the x and the y? And you see that you would need to add something to both the x and the y to get it to move in that direction. So if I wanted to move in this direction here, is the x going to be positive or negative? The direction. The x vector, or the forward vector, will be a positive number. What about the y? The y will be negative, okay? Because I wanted to move in this direction, which means I've got to add to the x and subtract from the y. Everybody see that? The actual amount that I want to add to subtract from the x and the y, we have to calculate. And we can calculate it by drawing this, which is a circle. It's just a not exactly circular circle. And you can then see that what I need to add to x and y is actually a point on the outside of this circle. Because this is obviously, this distance here is going to be 1, isn't it? This distance down to here is also going to be 1. And then this distance here needs to also be 1 as well. So what vector is going to be in this direction but of length 1? This is the question that we need to solve. And in a nutshell, because you guys already know how to do this, what will we use for this? Yeah, we could use Pythagoras, maybe not. We'll use the unit circle, right? And we can use sine and cosine from the unit circle. Alright, so to calculate this value for the forward vector x and y, you can draw a line across there, make a right angle triangle, like we've done lots of times on this course already. I presume we have done this lots of times, haven't we? Yeah. We have this angle theta here, and we can say that this x coordinate here, what's the relationship between x of this thing here and theta? Looking at the diagram, draw the right angle triangle. If I was to calculate this x, it would be the... Somebody say it. Will it be the square root of theta? Will it be theta to the power of 5?
It's the opposite side, so...
It's the opposite side of a right angle triangle. How do we calculate the opposite side? Sine. Okay, so it's the sine of the angle theta. Looking at this here, what's this here, the hypotenuse? What's its length? The length of the hypotenuse is 1. So if I have some angle theta here, and I want to calculate this x and y coordinates, that's 1. This is the x, so the x is the opposite, and this is the y, the adjacent side. So x is equals to the sine of theta, and y is equals to minus the cosine of theta. And why is it minus the cosine of theta? Because the y value here is negative, the x value is positive. And that's how you calculate the direction vector from this angle theta, which is going to tell us by how much these things needs to rotate. Does everybody understand this? So I've done this example a good few times for people. If you're still not 100% sure on the whole idea of the unit circle, I'll put up some Khan Academy videos, right? But we need to use sine and cosine to get this thing to point in the direction in which we want it to move. So let's add an extra field. So there's pause and forward. Let's add another float called theta. And let's say that theta is going to have an initial value of 0. Alright, so 0 is going to give me straight up value. And then down here in my update method, I need to calculate my direction or my forward vector. Forward dot x is going to be equals to the sine of the angle theta. And my forward dot y is equals to minus the cosine of theta. Okay. Forward. Alright, so there's x and y calculated, and at the moment, of course, all I'm doing is pressing the W key to move straight up. So, if the W key is going to move me straight up, then the sine of 0 is going to be what? Because what do I need to add to the x if I'm going to move straight up? So the sine of 0 is 0, and the cosine of 0 is 1. Okay, so you have minus 1, so that means you're going to move straight up. So, again, still nothing terribly exciting is happening, right? I'm still pressing the W key to move up. Now what I want to do is use the A and the D keys to control the theta angle instead of controlling the forward vector directly. So, when I press the S key, what I want is I want to subtract something from theta. And when I press the A key, I want to add something to theta. Okay, let's not worry about, sorry, not the A key. A is going to be moved to the left, isn't it? And D is going to be moved to the right. Let's get rid of S then, because S is backwards. So A should be subtract something from theta, and D should be add something to theta. There we go. So there's theta adding and subtracting. Watch what's going to happen now. What's going to happen now is when I press these arrows, you can see that it's now moving in different directions, but of course it's not pointing in the right direction now. I'm pressing these arrow keys and it's changing the value of theta, but it's not rotating in the direction that it's pointing. So there's one last bit that we need to add to this, and that's this render code here. Because what I now have is I have this variable theta that's controlling the angle that I'm moving in, and it's also controlling the rotation of the object. But now I need to actually rotate the sketch. I need to rotate the ship based on that angle theta so that it's also drawn in the direction in which it's looking. And that's actually really simple. All you do is you type rotate. Oh, hang on. It's slightly more complicated. Let's try some things here. Let's just try one thing. Rotate theta. Yeah, so the last four things we're going to use are rotate, translate, pushMatrix, and popMatrix, okay? So, let's just try this. Anyone tried it? Let's run the sketch and see what happens. Oh my goodness, look at that. That's what rotate is doing. It's causing the ship to rotate like that. Do you see it? What's the problem? It's rotating around 0, 0, isn't it? What we wanted to do is rotate around its own center of mass. Yeah. Oh, okay, no problems. Yeah, it's rotating around 0, 0, which is not what we want. We want it to rotate around its own center. It turns out this is a slightly... the way to solve this is actually in two steps. First of all, what you have to do is you have to get the object to rotate around 0, 0, and then you translate it into position. That's kind of a good way to solve it, right? So let's just put the code in for that. So first of all, let's imagine that the object is just going to rotate around 0, 0 first of all. Let's get rid of all of this pos.x and pos.y and just put in 0 instead. So wherever we have pos.x or pos.y, we can either get rid of it or just replace it with 0. Cool. Alright, so just even looking at the code, you can pretty much figure out that that's just going to draw the ship as if, you know, around the point 0, 0. So it'll just draw the ship like centered in the top left-hand corner of the screen now. But at least it will rotate properly now. The rotation always happens around 0, 0. So if I have it drawn in the center of the screen and I call rotate, it will rotate it around the top left-hand corner of the screen. So anyway, now if I run my sketch, you'll see that I'm able to press A and D, and you can see that the ship is actually up there in the top left-hand corner of the screen. I wonder if I've actually made a bug or introduced a bug. But can you see that it's actually rotating now around the top left-hand corner of the screen? Yeah. So last thing we need to do then is we need to rotate it and then translate it. The interesting thing here about processing is that these operations actually happen in the reverse order. So if you wanted to rotate and then translate, you have to call translate first and then rotate. So we can translate to pos.x, pos.y, and then rotate. This has the effect of doing them in the opposite order. So first of all, it will do the rotation, then it will do the translation. Well, I kind of know why that is. It's to do with matrix operations. Let's run it and see what happens now. So now I can rotate, and I'm able to move in the direction in which I'm rotating. So one of the sides is not getting drawn correctly. What one is that one then? Oh, that's probably the 0 side. So okay, yeah, I think that 0 one should be minus half width. Yay! Yeah, if everything is working, your ship should now translate and move correctly. And we've been able to replace all of the scalars that we had with PVectors, and we're able to use PVectors to get the object to move now instead, and to get it to point in the direction in which it's moving. So we're moving towards like encapsulating all of the behavior for this ship inside this class, and the behaviors become a little bit more interesting this week because we can rotate the ship as well, right? There's one last thing I would like to show you, and let's say I come over to here and I create a second ship. So this time I'm going to call the parameterized constructor for the ship. So I'm going to give it the position over 400 and down 400. But actually, let's do something a bit more reasonable. Let's say 100 and 100. And the other parameters that this ship takes, the W. Okay, so let's make this a different W value. Let's make this a W value of 80, so that we can see the differences between the two ships, right? So I've got ship1.ship.update, ship.render, and if we call ship1.update and ship1.render, then we should have both of them working. Okay, so now I've created two instances. The second instance of the ship, you notice that the second instance, the x and y coordinates are set to 100 and 100, okay, for the big ship. Can anyone notice anything peculiar about that sketch that we've just drawn? Well, just look at the position of the big one. Does it look correct?
100 or 100 relative to the small ship.
Yeah, exactly. It's 100, 100 relative to the small ship. It's not 100, 100 relative to the center of the screen. Look what happens now if you actually do the rotation. You can see that, you know, I've got the same key bindings for both the big ship and the small ship. So as the small ship is rotating, the big ship is also rotating around the small ship as well as rotating around itself. So this is not what we want, you know. We want these ships to be autonomous. That's the whole idea of making classes, is that we can make them autonomous. Can anyone figure out what's happening?
The bigger ship is on the center point of the center.
Yeah, the center point for the big ship is the same, is actually the small ship. Okay? So the big ship is being translated and rotated relative to the small ship. So what's happening here, you can look at the code and maybe it will make sense to you, right? When I call ship.render, the very first ship.render for the small ship is translating everything to the center of the screen, and it is rotating everything by beta. Then I come to draw the second ship. I've already done the translation. Translate and rotate will translate and rotate the entire sketch. You know, so what's happening here is that translation and rotating from the first ship is also affecting the second ship. Does everybody see why, you know, why that has happened? Translate, rotate happens once, the first ship gets drawn, then the second ship gets drawn relative to the first ship because I've already translated and rotated the sketch. Turns out there's a very simple way around this in processing, okay? As to add two extra calls. One is called pushMatrix, and the other one is called popMatrix. So what pushMatrix and popMatrix do is pushMatrix tells processing to go and store the current translation and rotation. So when my program starts initially, the current translation and rotation means no rotation, no translation. You know, because my sketch is just drawn. So that tells processing to go and store it, translate the sketch, rotate the sketch, do some drawing, and then popMatrix resets everything back to the way it was originally. So now when I run my sketch, the second ship should get rotated and drawn, you know, relative to its own position rather than relative to the first position. So, that's how we make autonomous classes to encapsulate things. You know, we've done some processing code to add to this, which is basically pushMatrix, popMatrix, translate and rotate. We've also taken all of the scalar code and we've replaced it with vectors. And we've made two instances of the class. So you can see now instead of having one instance, I've got two instances of the class, ship and ship one. And they're essentially autonomous classes, right? Because they all look after their own movement, they look after their own translation, rotation, and they don't affect any other instances of the class. This is an important principle of encapsulation, that the class should just do its own thing and manage its own state, you know, as much as possible. So I'll leave this example up here. I think we have about 15 minutes left, so I think it might be a good idea for you to try and write some code yourselves, okay? So here's a small modification to this you could try and make. Try and make another class. Call this second class, call it AI ship, right? Okay, and make AI ship move differently to ship. In other words, ship is moved by keys. What I want you to do with AI ship is have it move by itself. All right, you can draw it differently if you want as well. But what I want this ship to do is I want it to basically move around the outside of the screen. Once it gets to the extreme right, it should come down like this, and then it should move around like this, and then move around like this, and then all the way like that. So it's going to move by itself as opposed to the player movement. Is that okay with everybody? So that's the last 15 minutes. Just get started on that for today. Maybe we'll continue this in the tutorial on Friday, but why don't we try that, okay? And I'll leave the code up there if anybody wants to. You'll use it for your AI ship. Of course, yeah.